Okay. Yeah, so this is work that we've been doing over the last couple of years at King's, which is to look at issues around legacy software. I mean, there's still surprising amounts of legacy software in languages like COBOL, old versions of C, or VB6, which was mentioned, VBA. So there's a lot of this software out there which is still doing critical things. And for example, in the US a couple of years ago, some of the COVID measures were delayed by legacy issues with COBOL systems. And likewise in Australia, and so on. Even with more modern languages, it can involve quite a lot of work. Like
5 years. 5 years.
5 years?
Yeah.
Oh, wow. That must have cost a lot. Okay. So there's a definite use case there for the use of something, and we think that MDE can be useful in this. And why is that useful? Well, the point of going to a specification in, say, UML OCL from your old software is that then that specification can be code generated to a new platform and a new language. Now, some of the work that's been going on in other approaches, well, one approach that you see in tools on the web or commercial tools is to have like manually coded rules from one language to another. But if you do that for every pair of languages, you've got a vast overhead of work. There's also work in machine learning. There's been work at Facebook in the application of various machine learning approaches to learning, so mapping from Java to Python, Java to C, C++. These tend to use very large data sets from, say, GitHub codes, and there is always a degree of uncertainty about what rules have been learned. It's a black box, basically, what you've learned. So you can't produce a guarantee of correctness. Our approach has been to abstract from different languages, and we've actually done JavaScript, C, Java, VB6, and COBOL 85. Going to UML OCL, and then going to various target languages. These code generators already exist, so this wasn't new work. New work, the interesting thing really is to go from the source code to the model. So the translation step, first of all, abstracting the source program, and in a way that, as far as possible, tries to capture the precise semantics of the code, because ideally a business would want to convert the original functionality into a modernized version, but with the same functionality. For example, we're looking at some bond analysis systems written originally in VB with Excel. We want to translate those to Python, let's say. Well, we want the same functionality from the input. And forward engineer, of course, this code generation task is well established, and there's lots of code generators out there. So anyone can be used. We've got a set of our own, and you can choose virus or something. So that's the sort of picture on the source side. You've got various source code in various languages. Those are parsed by ACLA parsers for different languages into syntax trees. And then what's perhaps the most original thing here is we use a text-to-text transformation language called CSTL, concrete syntax transformation language, which takes those parse trees and generates text in UML OCL. Originally, CSTL was used for code generation, and it's used in particular to generate Swift and to generate Go. So it would take in this case, the parsed UML OCL and generate text code these languages, but I found it was also quite applicable to just working with actual parse trees. So, you could use other parsers, but Antler has a very large number of parsers for different languages. What does CSTL look like? Well, CSTL is based on pattern matching. So let's say we're taking in some C or Java, that could be either really, in this case. Do we have an expression that's a non-terminal in the grammar of the source language? And then we have a ternary choice expression with the underscores representing arbitrary subtrees. So they're like arbitrary expressions which have been parsed by the parser. And they could very complicate things, but here they're just represented as _1, _2. The translation on the right-hand side is the thing in the target language, text in the target language, in this case, anything else expression in OCL. And in this case, the underscore variables represent the translations of the things on the left-hand side. So, you know, it's a recursive thing. Translate this to that, translate that to that, and so on. So, I suppose the big advantage of this language is that it's something which a lot of practitioners could use and could write themselves and could modify themselves without being MDE experts. You don't need here to refer to metamodels. Indeed, metamodels are not built. Everything is being done at the level of parse trees with some annotations, for example, like types and so on. You can do this at statement level as well. Similar thing. I mean, I hope that's like immediately understandable by everyone. It's kind of doesn't need model transformation expertise or something. The same kind of thing in QBTR would be like a page, you know, for each role or something. And now, of course, you can't take OCL in its present form and translate everything into the OCL 2.4 because it's actually quite a restricted language. It hasn't evolved very much over the last 10 years, in fact. So we needed to add various things. We need to add function types. Most programming languages these days, they have function types. They have lambda expressions. You need to add map types, not even in the old OCL. So there's also a type of references, dates. So we need libraries, which are essentially PIM level. They're platform independent representations of things that you find in every programming language, like dates. And byte processing, types, reflection, exceptions, and so on. That's not everything, it's just like the core things that you might find in programming. One big issue is that in a programming language you have side effecting expressions. You have expressions which both maybe return a result and do an update, and simultaneously you can have non-referential transparency. So different parts of the expressions that are the same syntactically actually have differences. So we have to separately represent the update affecting query semantics. That can be quite complicated. As I say, only the core libraries can be represented. Java has simply colossal set of libraries, even in the standard library. Unstructured control flow can be very tricky. Typically, that's replaced by a function call. Now, as I say, the big advantage of CSTL, first of all, we used it for code generation because I have like decades of experience of writing code generators. I started off writing code generators in Java, then writing code generators in OCL, and finally decided to write code generators in CSTL, which is much faster. I consume less of my lifetime, which is only finite, in writing code generators. I spend all of my life writing code generators. So CSTL is a lot faster, and you can measure the time in person months rather than person years. And this is for abstractors, which are actually even more complicated than code generators. Something like COBOL, It's a huge language. I mean, they have like 50 varieties of add statement. They don't have assignments per se, but they have add statements, subtract statements, multiply statements, divide statements. You know, it's a monstrous language. So that was probably the most difficult job, but it still was done in about 2 months. Rapid generation. Fairly good coverage of the language for COBOL. It's up to about 80% as well. Now, of course, the interesting thing is, does it actually correctly translate some source to target? We use the computational accuracy measure from Facebook's transcoder work, where they basically ran a series of tests on each input in the source language, and then same tests on the target, translated target. For Java, we can translate to lots of different languages. For C, we're rather restricted because of pointers, so you have to translate to a language with pointers. The translation accuracy is quite good for, I suppose, the languages which are rather similar: JavaScript, Python, C#, Java. So we're getting in the 90s. For the more unusual languages, the percentage is not so high. What this represents is the automated process gives you like 3/4 of your work, and you may need to manually, then do manual translation. Okay, so if you look at some of the tools that you can get from the web, like Java, Python, they're not very good, and indeed they say they're not very good, but you can use it at your own risk. Transcoder has been at about 70% level. So yeah, I mean, machine learning approach. Although they're always having to manually write rules, you're still relying on the data sets, the quality of the data sets, and you can't really judge how good. MDE has been used, of course, for reverse engineering or re-engineering in the past. There's a standard from the OMG called the MDENet, reverse of MDA. And there are tools like Modisco and Remix. Generally, these based on building a big repository of data about the application rather than fine grained semantics. Okay. I think that's pretty much it. So we proved that this can be done. We're interested certainly in working with industry who've got these kind of problems, interested in these kind of issues, and looking at extending this maybe by using symbolic machine learning to learn the rules rather than manually writing instruction.
Thank you very much.